Hello and welcome to Cardano Dev Pulse, the podcast where we cut through the noise and bring you directly to the source. We're incredibly excited to launch this series with an unprecedented opportunity, direct conversations with the core developers building Cardano node. This isn't speculation or secondhand information. This is real deal, straight from the individuals sharing the very foundation of the Cardano network. We're here to delve deep into the challenges, the innovations, and the future roadmap of the node, giving you the inside scoop on what's truly driving Cardano's evolution. With that, today I'm joined with our co-host Carlos, and
Hey,
we
hello
have
everyone.
Javier from the consensus team,
Hi.
as well as Nick Frisbee from the consensus team,
Hello.
Marcin from the networking team,
Hello.
and Michael from the performance and benchmarking and tracing team.
Hello.
So with that, let us get started here. So Carlos, tell us a little bit about what we've accomplished lately, specifically in regards to the Plomin hard fork.
Well, I think everybody's aware right now, but in case you are not, we just came through the Plomin hard fork about a month ago, and that means that the entire Cardano platform, the blockchain, the protocol, everything is in the hands of the community now. So basically, that means that we are the most decentralized network, not only regarding block production, but also regarding governance. And also, not only the Plomin hard fork has occurred, but we have also enacted the constitution, the one that was approved in Argentina and Nairobi last December. It has been approved on chain. So we're really happy about that, I think. It's a milestone in the Cardano development, and I think it's a moment to praise all the developers, the engineers, all the product people, everybody in the community that was involved in this process. Congratulations. I think it is a great moment to be happy about that.
Have we learned any lessons from this that we can take going forward to future hard forks?
Oh, yeah. I think one of the main lessons I take home is the entire process that I need to tell it. You drove it really well as a head of product, Sam. You made it very easy for the community to get involved with SanchoNet. And that is a model that we should keep for the future, I think. Also, the early involvement of the community at every stage is another very valuable lesson. Starting from the drafting of the SIP 1694 all the way up to the testing and development of SanchoNet, and then all the way up to the drafting of the constitution that we just enacted on chain. I think the more the community gets involved, the more benefits we get as an ecosystem, the better Cardano gets. I mean, the community certainly made a lot of improvements to the SIP itself. And with SanchoNet, all the testing, kudos to all the people that got involved in testing with SanchoNet, especially Mike Honan, John Kelly, and many, many others. I think it was awesome.
Nice. So what action items do we have in particular for people that are listening to this in regards to the Plomin hard fork?
Well, the main one, I think, is because the system is now entirely in the hands of the community. I would say that the community needs to get involved. So you have, it's like call to action is, if you are not a D rep and want to become one, this is the time to do it. If you don't want to be a D rep, it's the time to actually delegate to a D rep, because the system really needs the participation of everybody, of all of us, to actually reach its full potential, right? So delegate your stake, your voting power to a D rep, or become a D rep yourself. That is like the main action that we all need to take right now, and get involved in all the discussions regarding the vision for the future of Cardano.
Oh, very excellent. Thank you, Carlos. Moving on into Genesis, which is an upcoming way of syncing the chain. Nick, would you like to give a brief overview of what Genesis brings to the community?
I cannot hear you, Nick.
Thank you very much. Yeah, Genesis was produced by the IoT researchers as an enhancement of Prouse. I think 6 years ago at this point it was published. The key problem it addresses with Prouse is how to sync nodes, how nodes catch back up to the network. The Prouse paper explicitly declared that it assumes that new nodes magically have the state of some existing node, right? So it sort of sidestepped the syncing problem. Obviously, you've been able to sync Cardano nodes even without Genesis, but that was based on some assumptions we made. Basically, the syncing node assumed it could trust its upstream peers. It could trust the peers it was syncing from. Genesis solves the problems that are introduced when you start to sync from peers that might be dishonest, might be adversarial. So as of Genesis, it is now it's a step towards decentralization for the syncing process. Now you can sync from the whole network, basically, or whichever nodes you happen to connect to, as long as at least one of them is honest and caught up. That's the key benefit of our Ouroboros Genesis implementation.
So that makes me guess, or perhaps wonder if it should be possible then that Prouse nodes and Genesis nodes can coexist at least for some time.
Oh yeah, absolutely, yeah. The researchers, the paper from Genesis, I think we'll have the link to share somewhere. It's on the ePrint archive, but it does a real, it's a crypto paper, so it might be difficult to approach. But for those who know the lingo, you can see that they prove that the Genesis protocol converges to the Prouse protocol gracefully as the node finishes syncing. So if your node is running Genesis, but it's completely caught up, then your node is indistinguishable from a Prouse node. That was one of our design constraints, right? We like Prouse. Prouse is important. The behavior of the caught up node is fundamental to the health of the network. So we did not want the Genesis implementation to disrupt that at all. But the researchers had already done the work. So they've ensured that the rules implemented in Genesis gracefully converge to the Prouse behaviors once it's done syncing. So yeah, they absolutely coexist. They're very compatible. Yeah.
That's good news, I guess.
Yeah.
Of course, because otherwise people would need to basically upgrade all the way at the same time, and that's not what we want, right? So we will have a smooth rollout phase and stuff like that. And perhaps Sam, you can comment on that.
Yeah.
Not only can they
Go
coexist, right, Nick? But like, so there is the Genesis mode, but when you get caught up, right, the node completely switches to a Prouse mode. So Genesis is no more working on the node, right?
Yeah. So the Genesis rules themselves are compatible, but moreover, to ensure this important property that we did not disrupt the Prouse behaviors, the code is architected so they're quite separate. So there is a moment where the node concludes that it's done syncing, and so it sort of flips and toggles and disables some of the Genesis components because it's caught up. Even though they could keep running and they wouldn't interfere, but we wanted it to be very explicit that the Prouse behaviors did not change.
Yeah, of course. Last time we checked, there were like 8 or 9 components for the Ouroboros Genesis, and one that really got my attention was perhaps 2 things that seem very important: the Genesis state machine itself and the lightweight checkpointing. And I think the lightweight checkpointing deserves a few explanations or comments about why it's important and what benefits it brings to
Sure. Yeah, that's a good topic. Yeah. So checkpointing is a general concept in blockchains that is generally familiar. I'd say Ouroboros, what is the exact word they use? Maybe moving checkpoint? I'm not sure, but it sort of, Prouse innovates on checkpoints in that it sort of sidesteps them and makes them unnecessary. However, for the Genesis deployment, or the introduction of Genesis, I did eventually, I didn't come up for a while, but eventually after talking to the researchers enough, it became clear they assumed that there would be a checkpoint for the historical chain. And then from then on, we'd rely on Prouse and Genesis so that we wouldn't need checkpoints so much. So to capture that, we introduced this so-called lightweight checkpointing, which is basically a whitelist, right? Limitations on which chains, which historical blocks the node would ever consider valid. And everything that's not one of those in that slot, right, is invalid. So it limits which chain the node can select. This is strictly unnecessary, right? We've done the due diligence. We've analyzed the historical chain. We've implemented the Genesis logic such that the existing chain is going to be the best one that Genesis will prefer. So in some sense, this is unnecessary. However, it is a good escape mechanism. Number one, it's very simple, and it provides that explicit checkpoint that the researchers were always sort of envisioning. So let's do what the protocol designers anticipated, because it's easy. Also, it's a nice little escape hatch. I don't remember the SIP number, but there's a SIP for the disaster recovery plan. And it does make mention of the lightweight checkpointing. So if there were some sort of disaster where the chain got very sparse, the lightweight checkpointing is an option that the community could try to use in order to sort of navigate that difficult time. Even if we're going to go back and do the recovery plan and fill in some missing blocks or whatnot, it's a good option to have on the table. And it was sort of bundled up with Genesis because, like I said, the researchers that's how they were thinking about specifically the Byron era, right? The pre-Shelley era, the pre-Prouse era. That's the kind of stuff they thought they'd just tuck behind a checkpoint. So that's the plan.
So one of the things you mentioned there was when the chain gets sparse. So why don't you explain a little bit how Genesis changes the consensus mechanism? In Prouse, we basically are dealing with longest chain. So how's that altering here with Genesis?
Yeah, good. That's a nice segue. The key rule from the Genesis paper is to use density to choose between competing chains instead of just using their length. I believe it's called a stake bleeding attack. But the notion behind this kind of attack that this rule mitigates, I think it's called a long range attack in general. And stake bleeding is like one way a long range attack could happen. But the idea is the adversary somehow creates a different chain that follows the rule of the current chain, but somehow over time, they're able to make it accelerate so that eventually it has more blocks on it than the true honest chain. And stake bleeding is like one of the possible ways that happens. I don't think anybody's actually sketched out how it concretely could happen on Cardano, but just the abstract risk of it exists. So to like nip that in the bud, Genesis says you don't just compare chains based on how many blocks they have. You also compare it based on basically how many blocks they have near their intersection. So when two chains diverge, there's a fixed amount of time slots in Cardano that we assess, and whichever chain has the most blocks within that horizon, which we call the Genesis density window. So you start from their intersection and you look at the Genesis density window immediately after that intersection, and whichever chain has the most blocks wins. That's the one the node should prefer. So the general idea is that a Genesis node, when it's syncing, as long as it has at least one honest peer, it will be seeing the honest chain. And basically, as a consequence of how Ouroboros Prouse works, the honest chain is always going to be denser than any alternative chain. Right? So as long as the Genesis rule just sort of limits how far it looks ahead when considering competing chains that it sees, and just considers that density near their intersection, then the Genesis rule provides the safety guarantees we want, which is our node will only stay on that honest chain as it's syncing through the history. And so it'll eventually catch up to the honest network. So I described the soundness property where we don't sync bad alternative chains, and we can use the density comparisons to avoid doing so, assuming we always have at least one honest peer. But there's also a liveness side, which wasn't really, that's not how people think about it. Particularly in the Genesis paper, they did not assume you always had at least one honest peer. They assumed you eventually found an honest peer. But there's some usability downsides there, right? Like we don't want a user's node to tell them it's caught up, but in fact it had. So And if they never found an honest peer, and so they synced an adversarial chain, how would they ever find an honest peer if the adversary controls the chain they see, right? So beyond the core safety property from the paper, I think it was Duncan Coutts and Agalos years ago in a bar on the back of a napkin, they sketched out how it would work. And it's slightly different from the paper in that we additionally assume you always have one peer. And then the liveness concerns of the Genesis implementation are ensuring that just that one peer is enough that you will eventually sync the whole chain and in a reasonable amount of time. Sorry, I think I got a little bit past the question you asked, but that's the nugget of the logic of what Genesis adds to. I was going to say adds to Prouse, but really Prouse has no logic for syncing. Prouse assumes it has modern chains, and it happened to be that if you only synced from trusted peers, then the longest chain was the right chain because you're only getting one chain. Trusted peers aren't going to give you different histories. They might give you different chains, but that's just because of Prouse, and Prouse handles that. So Genesis basically enriches the scope of Ouroboros from caught up nodes to also syncing nodes. Okay. Again, I lost track of the plot, but one more thing to say. There are other ways the node can sync, like the Mithril system, right? But even if Mithril were online and everybody loved it, it's sort of, I'd say that Genesis is more fundamental, right? Genesis is you sync the whole chain from scratch. Sorry, you can use Genesis to sync the whole chain from scratch to replay history as it played out. So that's a nice ability to have. Like maybe if you're paranoid, I don't know the details of Mithril. I'm sure they're ensuring safety if you do have a valid snapshot. But
Yeah.
Genesis is a more sort of fundamental protocol that can ensure that any node that runs Genesis will always be able to sync the chain as long as they can contact one honest caught up node.
Yeah, it definitely makes sense because assume Mithril is gaining adoption and every day more and more SPOs are using Mithril. But let's say suddenly Mithril gets off out of production or people stop using it, we can still have this certainty with Genesis, right? So it's a great thing to have. And regarding moving on a little bit, we know what benefit it brings, but in the practical side, how does it affect, let's say I'm an SPO, how it affects my operations, everyday operations, if I want to upgrade to a Genesis node? What do I need to do?
I'd say to best answer that, we'd have to get into some of the details of the rollout plan, which Sam is going to address. But I think at the moment, I can say that the Genesis logic is more in like a syncing node is doing more calculations now as of Genesis. The bottleneck should still be the validation of the block, right? So it's not going to go that much slower, and it certainly can't go faster. It doesn't skip any blocks, right? So the slowest bottleneck is the validation of the blocks. Beyond that, we are doing some additional calculation, and we're connected to more peers. Because as I've said a couple times, the assumption is you have at least one honest peer. If you only have, 10 peers, and let's say we're sort of skirting the threshold of how much stake is honest, then there's a pretty good chance that it's certainly possible that of thousands of nodes syncing every now and then, one of them is going to have no honest peers, right? So to make the possibility of a node connecting to the network and not happening to not find any peers very low, there's a whole system from the networking team called Big Ledger Peers that ensures that if we run with more peers, something like 30, 50, 100, then the probability of accidentally finding nobody honest is astronomically low.
Zero.
So
close to.
Can never call it zero, but it's never in your lifetime, right? So
so maybe I can. Sorry, Nick, you want to finish? Or?
I just want to say, so just the fact that we're running more peers, right? We're going to have some more overhead. So there is generally going to be a performance degradation for syncing. It should not be severe, especially because most syncing users are not syncing from scratch. They're just catching up the past couple weeks or the past month or whatever. So that's going to be a fast sync almost regardless, right? So Genesis does have a little overhead, but our we've assessed it, and it does not seem prohibitive, especially for the most common use case of catching up, for some months instead of all the years of the chain. There's a possibility that some users will suffer more penalty than others based on their throughput that they end up for the peers they find. So that's one of the reasons why our rollout plan is phased. And Sam can speak to that. Maybe Marcin wanted to go first, but okay, yeah.
Yeah,
I think
before we
that's
get
the
into
topic we should cover.
Before we get into the rollout plan, Marcin, why don't you talk about like how you actually get a list of peers into the node and that kind of tooling that you worked on?
Yes, so I'll get to that, but I'll just expand on Nick's answer and also Carlos's question. How does this affect SPOs? An SPO should have its relays or nodes synced up, usually or most of the time. So they will not be clients of Genesis. Genesis clients would be, full nodes relays like Daedalus. So they'll be the principal sort of load on the network. They do not, like Nick said, they do not have to sync from scratch. When you have a node or relay, offline for a few days or a few hours, it will be pretty quick and not present a lot of demand for bandwidth from the network. And at the same time, while Genesis is implemented in terms of these big ledger peers that the node maintains the connection to ensure that, is it on what is, ostensibly the honest chain, because we assume that these big ledger peers who collectively control 90% of the stake are a proxy for honest stake. So when a node is syncing up and maintains connection to those big ledger peers, the actual bandwidth to ensure that, what is their chain is not that big. The principal load comes from actually downloading blocks, so the node can sync up. But to download blocks, you do not actually have to download the blocks from registered relays on the ledger, these big ledger peers or other peers. These can be any other relays that you can contact, for instance, through peer sharing. So we can, in principle, also download these blocks from just some random node, as long as this random node agrees on the chain with these big ledger peers. So what I'm trying to say is that of course, the assessment of what is the expected demand for bandwidth from the network is still to be assessed, in the Genesis rollout plan. But it doesn't need to be something that is, severe. So it might be very acceptable, but we'll have to get to the details. So Sam, can you repeat the question again?
Yeah, so I was going to say, if you want to go into the practicals of how someone running a node gets the initial list of peers they're going to select from and the tooling to be able to generate that list.
Yes, so the question is that you are trying to sync a node, let's say from Genesis, without trusting anybody. So, when you start up a node and you do not have any relays that you know about that you can connect to, then that presents a problem because you cannot make any connection and you cannot start downloading any blocks. So you have to have an initial source of data that you can query and get some connections that you can start establishing connections. So this is solved by this mechanism of a big ledger peer file or a collection of peers that can be generated by a synced up node, and in the future could be released and distributed with a node release, and it can be signed so the community can trust it. So essentially, once you have this file, the node will load the data from it, and it will randomly select the peers from that file according to their stake distribution. So if a node has bigger stake in proportion to all the ADA out there, it will make connections to those peers. And there are various configuration options in the node that are available for users and relay operators on the CF Cardano Foundation's developer portal, which will be released once the next node version is released. So essentially, once you load this file into the system, it has a collection of these big ledger peers that are available to a sync node at some particular slot number. So let's say the most recent slot number. So even though it does not have, your node is not synced up and does not have any blocks or doesn't know anything about the chain, it knows that, oh, I can contact these peers from this file, which are peers which are ostensibly synced up, and I can query them. What is your chain? Can I get blocks from you? And also via peer sharing, what other peers do you know about? And I can contact those peers and potentially download blocks from those peers, which I mentioned that those peers that you learn about do not have to be the big ledger peers or any peers on the ledger. So you sample those peers, you start syncing the chain, and you get blocks from them. And in the Genesis method that Nick has just described, you follow that, and hopefully you end up on the honest chain. Like I said, I want to stress that the file contains not all the peers on the ledger, but just the big ledger peers. So like I said, these peers control most of the stake, so they are a proxy for honest ledger state. So the assumption is that they represent the honest ledger state at some point in the future, and you can trust those and get blocks and chain from them. That's pretty much.
I think the only thing I'd add is if your node hasn't been offline too long, then it has a somewhat recent ledger state, and so it will know this distribution. Like you don't have to go find a new big ledger peer snapshot file every time you want to sync. As long as you have a recent enough ledger state, then based on the idea that this big ledger peer set isn't going to shift radically abruptly in a short amount of time, then you just need a somewhat recent ledger state. So you started off your example talking about if somebody wants to sync from scratch, right? Well, that's years ago. So clearly the ledger state, the ledger, we didn't have relays back then, but suppose the chain started in Prouse, right? It'd have some ledger peers in it or some registered stake pools in the Genesis block, but that would be out of date, be years old. So it wouldn't necessarily reflect the current computers that are running that you could talk to now, which you need one of them to be honest the entire time you're syncing. So that's the motivation here for this file is, as Marcin said, from scratch, you need some up-to-date information because you need an honest peer today. But the key thing is if your node isn't too far behind, then you don't need to go get a different file. It just based on the notion that the massive amount of stake doesn't relocate abruptly. It could, but generally speaking, that would be a bad sign, I think, right?
Yeah,
so
it's not that
most
likely.
of the time. Yeah, most of the time, you don't need to fetch this file again. You can just use the one your node. And I think you implemented it such that your node does just sort of update this file as its ledger state progresses. Is that right?
No, the file is not actually updated. The file is static. So once you generate it, it is what it is. But like you said, once you start syncing up, and the closer you are to the current tip, if your relay node was only down for a few days or a week, it might be even more recent than that file. And you don't need the file at all because you can just use the most recent ledger state that you yourself have at that point and contact those relays. So if your ledger state is actually more recent than what is on the file, then you will use what is on the ledger. And the file will be there, but you don't need it. You only use the file if the information on it indicates that it is more recent than what is actually in your database of the blockchain, the downloaded copy.
Cool, thanks.
Yeah, so in summary, you only need this big ledger peers file if you are synchronizing from Genesis, from scratch. But once you have a recently synced node, you no longer need it because your node already has a snapshot. And
yes. And in the future, I think that there was talk about making this snapshot signed by Mithril. So this sort of provides more guarantees that I'm not sure how this mechanism would work, but I understand that this would somehow also secure it and make the community trust that this file that you get is actually what it says on the tin. Not just some random file. Or, we have some peers here that you can connect to, and they might all be fake. So
yes.
But you can always also, if you're an SPO and you want to use Genesis to sync up some node for whatever reason, you don't need to do that because you have your own database that you can copy. But if you wanted to use Genesis and this pure snapshot file, you can actually generate this file on your own, from your own node with a Cardano CLI command. So you can generate this file yourself, you can store it, you can move it to the machine with let's say a node that is in Genesis, blank state, and it will use that file to sync up or make the connections to the peers from which you will sync up.
So we've kind of really delved into this from a technical perspective and how it's going to work. I'd like to shift gears a little bit, Nick, and I'd like to have you go back a little further and explain, like, what did the development process look like for this? When did you guys start developing it? Was there any, from the research paper written, was there any other like architectural documents that were written, things of that nature?
Yeah, sure. So yeah, I looked it up. The paper's from 2018, I think, or at least or like it showed up on the ePrint archive in 2018. I don't know when it was published. So that's years, right? And I bring it up because like the original architects of our node, they were aware of Genesis. They didn't implement it immediately, obviously, but they knew it was coming. So there have been notes about it. People have been thinking about it. Duncan and Agalos had that bar envelope in the bar. Edsco de Vries, former architect, architect of the consensus layer, he sketched out he and I had been talking about how to do it before he left the project. But so it's been ongoing work for a while. I think I don't know when we actually when I took over and focused on this. I'd say maybe 2 or 3 years ago. That's just a guess, though. But that was the design side, right? And that was me and some members of the consensus team, like Javier or Alexander Eskin. We'd talk about it, try to figure out what it should do, go talk to the IOG researchers. We had a weekly meeting with like Christian and Alexander and Peter Gashi, Georgos, right? So that crew, and they'd help us refine our ideas, see if we've given them a compelling design that they agree implements their rule in spirit, right? We couldn't implement the rule they gave because it's in a very abstract level, right? They have to work at a higher abstraction in order to do the math and publish a reasonable paper. But to bring it all the way down to reality, we have to introduce a lot of refinements. And that's the work that's been going on for the past couple of years, and developing an argument that those refinements are justified, right? So that design is available. As a description of that design is available. It's on a PR that's been held up by some typos and some like to-dos. So we needed the Genesis code to merge so that we could have this documentation linked to the appropriate parts in the code, and those things haven't been followed up. But the PR is available. I gave the link to Carlos earlier, so I think that'll be posted somewhere in the comments of some.
Yeah, we will put it in the description down here.
In the description, yeah. Okay. So you can see there the overall design is described. And then the implementation has happened via a statement of work with Twig. So I'm a Modite. I'm a Twigger. Been that way for 6 or 7 years now. The entire time I've been on the IOG, or IOE, IOG, IOHK, the consensus team. I've been a member there, embedded full time. But in the last year or year and a half, again, I'm bad with time, so maybe it's been 2 years, but the statement of work approach to developing some chunks of the Cardano node came into effect, and there's a statement of work between, I think it started as IOG and Twig, but it ended with Intersect and Twig, right? And that was bringing on Twig to implement the design that we prepared over the previous year or two. And that was there's 6 of us. I'd love to attribute some names. It was a delight to work with them, especially because I stuck on the design side. I didn't really do the implementation. I was on that statement of work partial, just to sort of for them to pick my brain if something wasn't clear in the design, right? So the actual coding happened by a different set of tweakers. So that was Alexander Eskin, Nicolas Baquet, Nicolas Jeanreau, Facundo Dominguez, and Torsten Schmitz. And I'm very apologetic if I missed someone. The contract was worked out by Nicholas Clark and Chris Kowalski, and Clark also did some technical work. He's a technical guy, so we were happy to have some of his time for that. So that's where the implementation came. And that was done as a statement of work deliverable. It came with several milestones, each of which had a PR that delivered those milestones. And other members of the consensus team who are not Tweakers reviewed and approved those PRs. that's the process. That's how the statement of work was realized here. Was that the answer you were looking for to your question? I kind of spoke at
Yeah, I mean,
low level detail.
I think that kind of goes into the process a little bit there. I do remember I was invited to
Oh,
a
yeah.
workshop in Paris where we
Yeah.
kind of dug into this and figured out what it was going to look like.
Yeah. Also, just turning my brain back on here, I see Martin. So during the design phase, we spent a lot of time co-designing this with the networking team, right? Because as you've heard, there's plenty of elements about the eclipse avoidance, right? The whole idea was you could use this modified Genesis that depends on always having at least one peer. So that means a syncing node must not be eclipsed while syncing. And that's why we had some co-design with the networking team. So the networking team was involved in design, and also they implemented the big ledger peer stuff. So that eclipse avoidance mechanism was the networking team at IOG and then IOE. And then, yeah, so as part of the statement work for the Twig work, we organized a workshop in Paris. That's where Twig is headquartered, and it's centrally located for a lot of the attendees, except for Sam and I. But we got to go to Paris. So
Sorry.
there we had a nice workshop where we had the members of the Twig SOW team. Sam was there, so was Kevin Hammond. That they're sort of, I don't know the right title, right? But they're product owners on the Cardano side. And we also had Duncan Coots from Well Typed, and I don't think there's anyone else. And he sort of, like I said, back in the day, he had that folklore meeting with Agalos in the bar. So it was good to have him there to give us that longest term perspective as the Cardano node architect, the role he had for so many years. So yeah, I think that was 3 days, 2.5 maybe. And it began with us, like I just sort of on the whiteboard put up the design, asked all the technical folk in the room, who a lot of them have read the paper, a lot of them are hyper familiar with all the details of the node. And that was, let's just start with the synchronize. Here's the plan. What jumps out to you as suspicious and whatnot. And then we also needed to develop some of the details of one of the components, which was the chain sync jumping optimization. So that was the one where, again, this is something that Duncan had always sort of anticipated and had suggested and said, yeah, that'll be handled by the chain sync jumping optimization. And he had the high level plan for how to do it. Especially, it's fascinating that it can be backwards compatible with chain sync mini protocol the way it is. But the details hadn't been worked out yet. So that was the least developed part of the plan at that stage. And so for the second half of the workshop, we just sort of tried to figure out how that's going to work. I shouldn't say tried. It's in the past. We did figure out how it's going to work there. Yeah. So I think
so going
given the soapbox I have here, I just want to emphasize that it ended up being a very collaborative process between many teams, many groups of experts, predictable network solutions. I want to call them out as they're always present in the networking co-design talks. So yeah, lots of different teams and people and companies involved in making it come together in a way where we're all confident that it is safe.
Yeah, that's definitely something I want to highlight here, and we'll get more into it when we talk to Javier later on the next topic. But yeah, let's talk a little bit about what the next steps are here for Genesis. So essentially, we have this in the 10.2.1 code base now, and you need to have a big ledger peer snapshot basically to be able to work with Genesis. So in the short term, we're going to need to have some way to distribute that to people that they can trust. So that's going to have to be identified, who's doing the distributions, who's signing it, so on and so forth, to be able to get things rolled out. So what Genesis is replacing is the bootstrap peers that are split between the three organizations, IO, Emergo, and CF, that currently allow bootstrapping the entire network. And so once we have this available, then it's basically down to people starting to test it out. At what point do you think we can have the confidence that we make that the default level? And about how long do you think it will be before those bootstrap peers start to shut down?
Are you asking me? That's the kind of thing I would ask you.
Okay.
Maybe you're asking the community, right? So Like I said, I think I said it earlier, we're expecting there will be some performance hits. The sync times don't inflate prohibitively. Like I'm in the US, I have a residential normal internet speed and a normal internet speed for residents in the US, which is pretty bad, frankly, compared to a lot of the rest of the world. And, my sync time was a little worse based on some design, based on some of the changes that happened for block fetch in a syncing node, right? This notion that only one of your peers might be honest, we needed to tune how a syncing node chooses which peers to get which blocks from. And the conservative thing has some performance downsides if your bandwidth is too low from the nodes you're currently connected to. So there will be some hit, especially if you're syncing the entire chain, right? But especially if you're caught up, it's not that bad. If you have a better connection than the infrastructure, like in other countries often do, then you're not going to notice that slowdown. Right? As long as you can get the blocks faster than you can validate the blocks, then you're already going at top speed, basically. Okay. And for a lot of bandwidth, a lot of connections, there are a lot of pools, and pools certainly, but a lot of nodes, their bandwidth allows for that already. Especially when you get to later eras of the chain, where blocks are more expensive to validate because of Pluto scripts, right? So it's mostly the original era of the chain is where the slowdown happens. But most nodes only have already synced that part of the chain, so they're not going to pay this overhead. However, right, it's possible that some nodes around the world are going to notice this more than others based on their topology. So that's part of the reason we want to roll this out conservatively, right? We think it's going to be fine for most people, but we want to have those, intrepid users who try it out for us and let us know in the wild, did it actually do what we wanted it to do? Were the slowdowns tolerable for them? Were they intolerable? And we need to know about it. And should we prioritize doing some more work to try to tune up that block fetch so that it's more complicated, which makes it harder to argue that it's correct, but also maybe it can support, prevent the degradation to the extent that users won't mind it. So there's a couple questions that we can't really answer a priori. We need to just put it out there, ask people to use it, see how it goes. How long it'll take before we're confident, it depends on the number of volunteers we get to try it out, how much feedback we get, how many bug reports we see, how bad, like if it is bad, and we do need to tune up the block fetch, the new, like we call it devoted block fetch, although I don't love the name, but we didn't have anything else that we could think of. So the new block fetch decision logic for syncing nodes, how difficult will it be to get it to work for these people who can't handle the way it is, if they even exist. So there's some unknowns there, but it will work, right? They will eventually sync. It's just a matter of how much longer it takes. And I can't even expect it to be double, right? So there's it's going to be usable even in this first phase of the rollout, unless, somebody discovers a bug. But, it's just a big first step to get it out in the wild, have people who didn't develop try to use it, see how that goes, get the feedback on the interface maybe being confusing, right? So I really feel like the second phase of it might be the final. That's sort of a famous last words bold prediction to make in front of however many people walk this. But we've been working on it for a while. We're pretty confident in it. It's worked on all our tests, right? So really, from my perspective, the main phased rollout is to see how bad the performance hits are for individual users that we have not been able to emulate as the devs, right? So,
so definitely we will need community involvement and volunteers to test it out, and that's where the rollout phase comes to place, and perhaps it's time to talk about it.
I'd like to also expand on that. We in the networking team have also been running some sync tests, and from a single user perspective that's syncing from scratch, the difference between Genesis and Browse is actually on the order of minutes, tens of minutes. In the time it takes a node to sync up is like 19 to 20 hours. So Genesis might take 15 or half an hour longer. So on that time scale, the performance for a single user is actually something that is not, in my opinion, significant. The big question is, what is the actual load on the network? Because IOG, CF, and Emurgo will be at some point potentially retiring the bootstrap peers. So the question is, when everybody is starting to sync up from scratch, or there is some unanticipated network downtime, and more people just get online to sync up, then what kind of load will Genesis present to the big relays, the big SPOs, and other ledger peers? This question is difficult to answer ahead of time, so we will have to do some studies internally, and this will be most likely part of the Genesis rollout plan. It will take some time.
But I would just looking back at previous rollouts, so the P2P rollout, that took a fairly long amount of time to basically get everyone switched over to using peer-to-peer. I think this is going to be much lower scale than that. Would you agree with that, Marcin?
Yes, I think this is likely. The P2P switch. This was actually before my time, but I understand this took a while. This rollout plan and some testing potentially it might take a number of months, but I do not anticipate a long drawn out thing like, let's say, with peer-to-peer, because essentially Genesis is done. All we have to do is do some testing, performance wise, things like this, and so we just have to measure how it actually works, in a bigger setting.
I think it's good to mention, there's a particularly clever part of Duncan's original idea, which is this chain sync jumping optimization lets us have more peers without putting a linearly corresponding amount of more work on the servers on the peers we're syncing from. But part of that is only so. An interesting part of that is Duncan's design for chain sync jumping was backwards compatible, in so much as you could sync from a node that didn't know about Genesis, right? It will it'll give you the right answer, even if it doesn't know about Genesis, but you do. So that's part of the reason the rollout can be more flexible. Is things don't happen in lockstep, right? It's not like the whole network needs to be ready to go to P2P, or go to Genesis at the same time. And then the last thing, I don't know if I said this at the beginning. I just wanted to emphasize, this is all overall part of the decentralization part of the big Cardano roadmap, right? So now you can sync from the network instead of syncing from the bootstrap peers, which are a nice service provided by Cardano Foundation, Mergo, IOG, everyone else. But fundamentally, that's some degree of centralization, right? So that's what we're trying to eliminate, and what Genesis lets us finally do. So capital D, decentralization. Getting Cardano done, right?
Exactly.
So, okay, but I interjected, so I'm done.
So I think from there, we can probably move over to UTXO-HD and talking about the development there. Let's flip that one around this time and actually start with the development path of how we got. When was the idea first envisioned? How was it formed? Was this through formal research, or was it more on the engineering side? Let's just let Javier tell the story there.
Right. So I started working on UTXO-HD, I think it was 2 years ago, a bit more than 2 years ago. And before I started working on it, I already got a design document done by, I think it was Duncan Kutz.
May I interrupt you just a second? Some people in the audience may not know what UTXO-HD means.
Right.
Let's start from there.
Okay, let's start with a high-level summary of it first. That's a good point.
All right. Okay. So the high-level summary of UTXO-HD is, so right now a Cardano node has to keep all the UTXO set, all the ledger state in memory, right? It actually has to keep K ledger states, which due to some features of Haskell are not K different ledger states, but it's just one big ledger state and modifications on it, right? But it has to keep a fair amount of stuff in the memory just to keep the chain running and to be able to perform rollbacks on the last K blocks of the chain, right? So because of this, the node is a very memory intensive process, right? And this is just bound to keep growing into the future. As soon as we get more UTXOs, more activity on the network, this will just keep growing, right? So there was an interest on taking part of that data that lives in the ledger state and putting it on the disk storage, right? Moving it into the disk allows frees a lot of memory, a lot of RAM in for the process, right? There are a bunch of stuff in the in the ledger state, which actually can be moved into the disk and actually like evolves once on each block, so you don't need like to have it always at hand, right? Furthermore, there is like some features of that data, some properties that allow you to treat them like to compute the differences in those in that data, right? Instead of like you can even have an algebra of differences. So there were some parts of the ledger state which were suitable for moving into the disk, right? And in particular, one of the main ones is the UTXO set. The UTXO set is the like a big data.map or a big map that maps TX in to TX out. So every single coin, so to say, that exists in Cardano is in the UTXO set. And that one was moved, or the UTXO-HD project takes that one and puts it on the disk instead of living in RAM.
Memory.
Right.
Which is gigabytes of.
Yeah, it's gigabytes. Yeah.
Yeah. How much it saves? Just as
So I mean, there are
estimate.
So there is still like no official numbers, but on my machine I was able to save, I don't know, 12, 13 gigabytes of RAM.
Okay.
By using the on disk backend.
That's a lot.
Which I will probably explain later, like how it actually works and what is the idea for the future for it. But yeah, so that is overall like the idea of UTXO-HD.
That seems. Sorry. Go, Marcin.
Is this something that you can switch on and off? Let's say you're running a block producer node. Is this a node that you want to have UTXO-HD on, or do you want to have everything in memory?
Right. So we actually developed UTXO-HD so that it can have different backends. Right. One of those backends is what we call the in-memory backend, and that one has kind of like a similar memory consumption and performance as a pre-UTXO-HD node. Right. It's just like internally, the consensus layer has just been like reshaped to make use of these like differences on the UTXOs and so on. But in general, it should be as performant, and actually the benchmarks seem to indicate that it is as performant as a pre-UTXO-HD node. The downside for that one is that it consumes as much memory as a pre-UTXO-HD node. But SPOs right now, in principle, are able to run the node with those requirements. So in principle, they want to have like as much as fast node as possible as they can, right? So the idea is, at least for this first version of UTXO-HD, the on-disk storage, the on-disk backend, has some performance penalties that the in-memory backend doesn't have, of course, because we have to go to the disk, read stuff, write the new UTXOs, and so on. So probably SPOs will still want to use the in-memory backend of UTXO-HD, and people that have, for example, I don't know, a Raspberry Pi, they should be able to use the on-disk backend, right? Run their Cardano node in a machine which is like much affordable than like a multi-gigabyte RAM machine, right? And still follow the chain. So the idea is, yeah, for SPOs probably they will need to use, or they will be themselves interested in using the in-memory.
Yeah, because they need to validate transactions, so they need quick access to those UTXO sites.
Exactly.
Right?
The
So
end user, the user can use the disk backend because he does not need the performance, right? So he can still use his computer for other things and have a lightweight sort of version.
Exactly.
Okay. Seems like a feature that could enable full node wallets again to be usable and everyday random consumer level machines rather than needing 24 or more gigabytes of RAM, right?
Yeah, exactly. And actually, this is one of the goals, I guess, of Cardano, right? It's as Nick mentioned, to have for it to be as decentralized as possible. And one way to achieve this, or to increase this decentralization, is for people to be able to run the node in weaker machines, so to say, right?
Lowering the system requirements in order to be a participant.
Yeah.
So I just want to clarify, certainly, making a full node wallet more viable is this is a big step towards that. This is the first step of UTXO-HD. we're moving the UTXO map to disk. There are other parts, like Javier said, the legislate we could move. Those haven't been moved yet, and that'll be later work.
Well, before we get
be
into that,
necessary before the full wallet stuff becomes viable. But yeah, I did want to get it back to Sam because he was going to start with the development process.
Before we get into that, let's talk about the development process. And then, I think before we start talking about that, we can also talk about some of the things that are integrated, getting ready to be integrated now versus some of the things in the more long term. So let's go back to the development process and how this all started.
Right. So when I started working on UTXO-HD, so before I started working on UTXO-HD, I was actually doing some small experiments on Genesis, right, on the very, very early stages of Genesis, like generating some test cases and so on. And before I started on it, there was already a document that I think you, Nick, Duncan were involved in designing that document, right?
Yeah. So I'd say UTXO-HD efforts was on my plate at first, but happily I eventually gave it to Javier, who did a great job carrying it to reality. But in the original, I don't know when, it certainly became a hot topic when I don't know who, but someone noticed that the legislate, right, was the UTXO map was getting bigger and bigger. I think Cardano saw some uptick in adoption or something. And we realized, our memory requirements are becoming more painful for users. And that had been anticipated, but I think it did happen sooner than we thought it would. I think maybe Cardano blew up a little bit or something at the time. I don't remember the details.
That would have been the Mary era when we introduced native assets. And
I'm guessing NFTs.
People love NFTs.
Yeah, that's probably that it suddenly ballooned, and so we had this notion of it looks like we're going to be approaching the 16 gigabyte cliff or whatever soon enough, and then all of a sudden we were pretty much there. So got caught a little flat-footed there, but we live in it's an exciting space, and you can't always predict how blockchain is going to evolve. That'd be boring. But right. So at that point, it became sort of a scramble to see how quickly could we get this to work. And like I said, it'd been anticipated. Again, Duncan had ideas about how to do it. And so I think the work spun up there. And part of it was we wanted to use some off-the-shelf tooling, right? So we did some triage assessment of things, and it looked like LMDB was the backend we wanted to use to maintain the data on disk. I think Javier will probably later mention that is still the case. That's what we're delivering in this first one. But because of how timelines have worked out, we might not be sticking with LMDB too long. But it is the current vehicle for the backend on disk. So, right, assessing which options we can use, we went with that path. And so LMDB, I don't know the terminology here, but unlike the alternative that Javier is going to talk about, it basically meant we needed to have exactly one set of UTXO on the disk at a time. And that's why this design from Duncan, and I feel really bad. There was another guy. I can't remember his
Douglas
name.
Wilson?
Douglas Wilson. Great. Yeah, they wrote up the design for how to maintain those K+1 ledger states that Javier talked about, the differences between them all, given that the oldest one was stored on disk. And so we had this really cool design document based on sequences of differences, and like Javier was saying, the algebra you can use to query and find the right set you need for some transaction based on those differences in memory and the actual set of historical UTXO on disk, right? That's where we started. And I don't remember what happened. I think Genesis maybe spun up, and so I switched and focused on that, and then Javier took over.
Yeah. So at that point, Nick already created like a first prototype implementation, just with the types here and there, and like some stub functions that sketched how this could look like. And just getting, so from that design document, we started implementing. I think it was me, Joris, Pavel, even when he was with us. Like, it was a joint effort, right? It was yeah. So we started implementing like the DB changelog, which is this structure that Nick mentioned that keeps this sequence of differences, right? That we can then like forward values through its it's kind of like for the volatile part of the chain, instead of writing stuff to LMDB, you keep it in memory, right? And from time to time, you dump it into the database. So we developed that first version of UTXO-HD. We benchmarked it, and the results were like the node was functional, it was fully functional, but the performance was not comparable with the pre-UTXO-HD node. Right.
And this is the in-memory backend, just to clarify on that.
That was the V1 in-memory backend. So,
and also I think the V1 on disk backend didn't save as much memory. Like I think the differences took up more memory than we thought. So some of the savings was lost. Yeah.
So it didn't really like look very good, but at that point. But while we were developing UTXO-HD, well-typed, there was a statement of work with well-typed that they would develop the library LSM trees. So LSM trees is a database for the disk, right? That, to put it in a like super simple way, it writes files to the disk, and from time to time, like those files are merged into bigger files, right? And you have some filters, some functions that are able to tell you like this value is in this file or it's in this other file with like, well, I think it actually can tell you like it might be here or it is definitely not here in this file, right, Nick?
Yeah, I'm blanking on the name of the data structure, but it's sort of the most famous. Oh, Bloom. It's a Bloom filter.
Bloom filter, yeah.
Yeah. So, you know, it doesn't have false negatives and false positives. It has one of those, and you can design around it.
So this LSM trees library is still being developed. It is bound to be like finalized this year. And we actually took. So LSM trees has a main difference, a very big difference with LMDB, as Nick mentioned. LMDB only allowed us to have like one UTXO set on the disk, and that particularly means that we had to keep the UTXO set for the immutable part of the database, right? We could not write stuff from the volatile chains because those chains are not permanent, right? And are not immutable. So we were forced to keep this like very long sequence of difference, and like every single value that we wanted to read had to go through this sequence of differences, and that was just like a lot of computation for nothing, so to say. I mean,
I think maybe we could have introduced like a Bloom filter there to help us optimize that away. But at that point, we're kind of starting to implement some of the LSM logic as a hacks so that we don't, because we didn't have the LSM tree database yet. So so the LSM tree was sort of always on the timeline, the plan for UTXO-HD, but we thought we'd be able to deliver the LMDB node sooner than the LSM tree backend would be available. And then, as Javier said, you know, unpleasant surprise, there was more overhead there than we thought. And nowadays, it looks like we'll be delivering it sort of shortly before the LSM tree is available. Sorry, but you can go ahead.
Yeah, so the in-memory implementation that we had at the time was mirroring what LMDB was doing. But actually, when we thought about it, and we thought how we were going to implement LSM trees, we realized like we didn't need to follow exactly what LMDB was doing in memory, right? We didn't need to keep those differences because we didn't really have a UTXO set at the immutable tip, right? So we were just, we had an in-memory implementation of LMDB, so to say, right? And actually, we could just like go back to the design that was there before UTXO-HD and just like tweak some stuff that would also work for LSM trees and make that into an in-memory backend for UTXO-HD. And that one is the one that is actually as performant as the pre-UTXO-HD node, or so say the benchmarks. We still have to do some testing. This was on a previous version of the node, so we still have to like rebase the development and make sure that everything works. But yeah, we now have like V2, so we call it V2 in memory. We will have V2 LSM trees, and we have for now V1 LMDB, which is the one that we are going to deliver. And like after some things that we have been optimizing, that one didn't look bad on my machine recently. Like that is the one I said before that had some savings of 13, 15 gigabytes of RAM, which is like surprisingly a huge amount of RAM. Right?
Yeah, that's a lot of saving. It's impressive. And
So
And-
with the LMDB version, just wanted to mention that some time ago, so after that, there has even been some more improvements, but some time ago, I was able to run it on my Raspberry Pi. It's a Raspberry Pi 5 with 8 gigabits of RAM.
Mhm.
And I was able to run the node, and the node was able to keep up with the network,
Well,
which
nice.
is, I guess, very good news.
Very good news indeed.
So I think one of the things that we want to kind of point out here is that, again, this is coming across multiple teams. Like Nick Frisbee started with it on the Twig Modus side, and Duncan and his team on the well-typed side basically picked up the LSM stuff. And you yourself are with well-typed, I think, but you're contracted by IO Engineering to basically work on consensus, and you implemented this stuff in here there. So, I mean, I think that's something that we really want to emphasize here and point out in this long arc of looking at what's being developed, how broad the ecosystem in developing it is already, and how it's not necessarily just a single centralized entity that's making these decisions and coming up with these ideas. And the other side of it, I would, sorry.
I was just going to mention, following what you're just saying, we even discussed stuff also with the networking team. We also discussed a lot of stuff within the Ledger team, because for us, the Ledger is just something that we call and validates transactions or blocks, right? But having to manage these UTXO sets, we had to understand how the Ledger makes use of them, or what do they expect from consensus, right?
Of course.
We also discussed it with external people, with people implementing other nodes. How are they doing it? So we have been, this has been a joint effort by many people again. I think the big PR is in the Ouroboros consensus repository, because that is where many things in the code change. But many people from different teams have contributed to this.
And the other reason I wanted to bring in for this first episode here, talking about how these teams work together. We started with Genesis, and now we've gone on to LMDB. And one of the unique things with the UTXO-HD in general, not just LMDB, but the UTXO-HD arc is it did not start with research. That was an engineering effort. That was an implementation that engineers were like, hey, we can optimize this. So not everything necessarily has to start with research. And I think that's something we want to emphasize here as well.
Yeah,
so,
definitely. So this was developed, I think, as Nick said, by Duncan and Douglas. I think they were the original designers of the first solution of UTXO-HD. And even though there is this design document that has some mathematics there due to the algebra and the proofs of the algebra, yeah, I agree that it was mainly an engineering effort, this one.
So going forward here, what's it look like for people being able to start using this? Is this like a long ways out, or are we looking at a pretty short term to be able to start using this LMDB and in-memory UTXO-HD implementation?
So I think it will not be the next version of the node, but the one after that will come with UTXO-HD, right? Just a warning, UTXO-HD will replace the previous version of the node. So once UTXO-HD is merged into the node, and this feature, after being tested and so on, there will be no UTXO-HD node, right? There will be either UTXO-HD in memory or UTXO-HD on disk, right? So we will be releasing in a couple of versions of the node. For people that actually want to try it out, there is at least a version that builds on top of Node 10.2.0, I think it is, which is the mainnet release. So
I just built it today, so it compiles.
Okay, good to know.
Yeah.
So we will be rebasing those changes on top of the version that we prepare, and probably at that point we might even announce that the binary is there if people want to try it out. Apart from that, people that actually have a database like a ChainDB, so for example, say am I an up-to-date node, right? And I want to switch to UTXO-HD. I will actually have to change the format of the ledger snapshot. Right, the ledger snapshots will not be compatible between like a legacy node and the UTXO-HD node, either in memory or on disk. Like even between those two, they are incompatible. Right. So we will provide a tool that you can use to convert your snapshot from the legacy format into the in-memory format, or even into the on-disk format. Right.
Yeah.
Say I have a super powerful machine. I'm running the node. Everything is fine. But I also have a Raspberry Pi that I want to put to work. Right. I can convert the snapshot in my big machine and just copy it to the Raspberry Pi and start a UTXO-HD on disk node. Right. Before we even get to like release all this, this will have to be benchmarked. Benchmarks will have to look like healthy. The performance should not be degraded. We like in the latest round, it looked like that. Probably Michael will speak a bit more after that, after I finished. But yeah, so in general, the plan is in a couple of versions of the node, expect UTXO-HD to be released.
Nice, and that conversion tool is really promising because that saves you from going to synchronizing from scratch. So
of course, if people don't like, people can still just synchronize from scratch, or like the UTXO-HD node is just a normal node in the sense that it can sync with the network as any other node can, right? So you will be able to sync with the network with Genesis or with or without Genesis. That is like orthogonal to UTXO-HD.
So like, if you don't want to bother with the conversion tool, you can just start the UTXO-HD node. It'll see, I can't parse that snapshot file, and it'll just replay the blocks in its database, which is a lot faster than a sync, right? That's just hours.
Yeah.
Or you can just start one fresh, and then it'll sync from the network. But the tool is there for convenience if you care to bother with, an extra script invocation in order to make it quicker. It saves you, however long it takes to replay the chain, which is hours.
Last time I did a replay, it was like about 5-6 hours.
Yeah, but like if you don't care, then you don't need to bother with the script. But if you do care, then the script's there for you.
That's lovely. And want to switch gears to, Javier has talked about several times about benchmarks, and perhaps this is a time to bring Mikhail into the scene, Sam.
Yeah, so Michel, why don't you give us a little brief introduction about how we benchmark nodes, what we're looking for in it, where the people can find your reports, how things iterated, especially in the UTXO-HD side, with the implementation and the benchmark results.
Yeah, of course. So that's a lot of points to cover. So let me start by talking about benchmark means we want to observe certain things. Okay. So one of the things that my team does is providing the tracing framework, the tracing system for the node that adds the pervasive observability throughout the system. And it's important that you can really observe traces understood as evidence of program execution. It's not logging.
What the node is doing.
It's not just measuring from the outside. So let's look at, how much RAM does the process take, or how much CPU cycles does the process burn. It's really, we want to have like a very fine-grained, configurable way of getting evidence to observe a system running under, controlled conditions or conditions in the wild. Okay, so this is how we do benchmark. We, from all the observability that's built in, we select those traces, that evidence, which lets us build an analysis and timings of system behavior. So that's all very abstract. Maybe I can give you an example of how that typically looks. For any given node version or feature branch, we are able to deploy a custom environment of nodes. that stretches across different data centers on the planet. So we have an actual network with latencies. We restrict the topology. So what we want to do is we want to make it very difficult for the system. So this means we want a block to travel along difficult paths until it can be adopted by all nodes of the cluster. We just don't want to take it the easy way out, because then we have a problem with topology that's dynamically optimizing, and then it's hard to reproduce the measurements. So that's of course a condition. So imagine we do this benchmark on some commit and we do it 5 times, and all the times we get different measurements. So then you don't really have anything to compare. So we need to be very restrictive in that environment. What we're looking for so I've mentioned this before, we are looking at, well, resource usage. We are looking at forger-related metrics. So this, of course, targets block producers mainly to see, so how quick, like most importantly, when the forging loop is started at slot start, and a node becomes a slot leader. So how long does it take until this node is able to announce the new block header to the network? So that's a crucial measure here. And then we go from there and we build small intervals. So this from slot start, all the steps down to announcing the new header. We look at peer-related metrics. So we measure for a certain block hash, like from first announcing the header and then fetching the block and the body and so on. How long does it take to diffuse that block to a certain
first peer
of the network? Yeah. So how long does it take to go from peer to peer? And then in the end, of course, we measure how long does it take to be adopted by the network, by the entire cluster. Yes. So this means when we have these centiles, so 50% adoption, that means 50% of the cluster nodes have adopted that block, and 80%, 96, 100%. So this is how we get comparative measurements. So we can compare one commit against another commit, one feature against the absence of that feature, and so on. So this is what we are looking for. We do comparative benchmarking, focusing on spying regressions. Carlos.
And
So
measuring this, sorry, go ahead, Sam.
I guess one thing I would ask here, so you're talking about comparing feature to feature. What about node implementation to node implementation? Is this limited to just Haskell nodes, or is there a way that basically you could use this to benchmark one node against another node for an apples to apples comparison?
So that's an excellent question. So for an apples to apples comparison, this is possible in theory when the observability that's built into the systems or the nodes uses the same semantics. So if we emit the same evidence at the same location in the code or on the same logical path to block production, diffusion and such, then it is possible to get comparable results between different implementations. Of course, so as the traces that we emit and that we use for benchmarking. So this is open source. So in principle, it's possible to equip other node implementations using traces with the same semantics. On the other hand, there is the excellent Cardano updates blog where we publish our reports. I mean, not all of them that target different kind of feature branches or experiments, but we always publish mainnet releases. So maybe I guess you'll find a link in the video description to the Cardano updates blog, where under the section reports you can find the benchmark reports, and you can have a look at what metrics we're measuring. And there's a summary and a conclusion for each report to see like what the analysis process has yielded.
Javier.
Okay, so I just wanted to mention, like, in regards of what you said about other implementations, that the traces are actually emitted in JSON, right? So, like, it's not some Haskell magic that we are analyzing. It's
So,
like traces in JSON that can be emitted in any other language. So
yes,
if they
that's true.
implement the same
And
traces, we can just like compare and see how much time it takes on different parts of the code.
yeah, Javier, you're completely right. That's the surface representation. So we happen to have a JSON as a surface representation, but that's not necessary. So when you have the same semantics, you can translate one representation. So, for example, some process decides to emit open telemetry data, and we got this batched up, like 10 gigabytes of open telemetry data. We can translate that. But as long as the points where the open telemetry events are emitted have the same semantics as our tracing system in the node, in the Haskell node, that is. But maybe to give you an example, so Nick previously talked about the aspect of Ouroboros Genesis performance when doing chain sync. So what my team is doing in that regard is we are making sure that once the protocol is in the caught up state, so when Nick claims now they will behave equally, then we actually measure that they do. So we have that cluster of nodes running a benchmark once in the Prayos mode, and then with the exact same settings, just switching it to Genesis mode. And then we see that they are caught up. And then from then on, we want to see that the metrics do not diverge. I mean, not statistically meaningful, at least. And they don't. So we've seen that in the benchmarks. And this means we are not just claiming, but we have evidence that Genesis mode and Prayos mode, once all nodes are caught up, there's no performance impact between them. And Javier has been talking about UTXO-HD. So let me give you a quick perspective of how that looks from a benchmarking side. So we use different workloads to stress different aspects of the system. And one workload with the LedgerDB version 2 implementation that Javier spoke about, one of those workloads was stressing the UTXO set in particular, and we saw that one forger metric regressed meaningfully. So this means that for diffusion, everything is fine, and for other conditions, everything's fine. But just when you stress the UTXO set that way, one metric for a block producer would regress. So by having those intervals in the forging loop, we could locate it very well where this was actually happening. In this case, it was taking a mempool snapshot just prior to forging a block. Our team could provide a synthetic chain to Javier. This synthetic chain was filled with exactly those kind of transactions which caused the regression. So, and then by using a tool to like basically replay that chain by adding all those transactions back into mempool and reforging the blocks, and doing so on that synthetic chain. I mean, not even running a node, just running a tool that incorporates the consensus component of it. He was able to find that regression in the code and change it, address it, validate it on that tool, and then give it back to us. So we said, let's run it again on our cluster and validate that this is the fix, that it is really the fix, as we would predict from having the synthetic chain, and it was. So this is the way that we interact when we find something like a regression of that sort. Summarizing the UTXO-HD, and I mean that's not a small feat, because what Javier told basically is that you get an extra layer of abstraction in the node, so you're able to abstract over backends now. You get an extra layer of abstraction without any performance penalty. So that's something good to achieve. And we've seen that the in-memory backend, well, the current regular node does everything in memory. So when you add this layer of abstraction and still keep everything in memory, you do not have a performance penalty. And now what you gained by that is you can switch out backends, for example, by using a or different on-disk backends. The important thing is that when you have everything in memory, as would be the case for a block producer, because you still need that efficiency, we can now say, because of the evidence that we have, that for a block producer, a network of block producers really, this would not mean any performance impact to the network. And we are able to quite reliably predict a slight difference in resource usage, which means that the UTXO-HD in-memory backend currently will use a little bit more of RAM, as Javier pointed out, but it will be slightly more CPU efficient. Also, the report on this UTXO benchmark, it's also published on Cardano updates, so you can find it there.
Yeah, I'll find the link below.
I think this is probably a good place to wrap up here. So I want to thank my co-host Carlos. I want to thank our guests Michel, Nick, Marcin, and Javier. If you are watching the recording, or if you're watching this, or if you're watching this live, reach out to me or Carlos if you have any topics you would like us to bring in some Node developers to come discuss. I do want to leave saying that this is, while these are all employees of IOG and other entities, this podcast does not necessarily reflect the reviews of those entities. And we look forward to our next one that will be announced here in the future. Thank you, everyone, for joining. Is there anything anyone else wants to add before we close here?
Yeah, just a very quick appraisal again to all of you guys. Thank you for joining us. It's been great having you as our first guest. You are all my superheroes. I respect you very much. And thank you for being our first guests. And hope to see you around next time. And
yeah, definitely. Thanks for having us.
People enjoy that.
Yeah.
Let us know how you think about listening this time, but hopefully we will have more ways to communicate with you guys, listeners, in future episodes. But yeah, let us know what you think in Twitter or trash us in private. Thank you.
Thanks, everyone.
Thanks a lot.